All right, next up, we're going to take a look at some types of solids. There's many ways to classify these. And really, the properties of solids are highly dependent on what they're made out of. And especially, with like electronic or magnetic or optical properties, all of these are really important, but they really depend on what your solid is. So we're just going to take an extremely surface level look at this kind of stuff. We're not going to go in depth at all or even really do it justice. A lot of my PhD work was on solids, and they get really complicated really quickly. Of course, we're just in general chemistry, so we're just going to learn the very basics. So the first type of molecular solids are the first type of solids are molecular solids. Molecular solids are made up of individual molecules held together by what? Well, if they're individual molecules, then they're only held together by intermolecular forces, right? So an example of this is ice, right? Ice is just individual molecules of H2O that are held together with their intermolecular forces. A lot of other molecular solids, again, something like a sugar cube, right? That's made out of individual molecules of sucrose. And if we think about what we said about intermolecular forces, we said they're much weaker than chemical bonds. And so they're pretty easy to break apart. And this results in molecular solids generally having low melting points. And that's because these intermolecular forces are much weaker than bonds. Next type of solid are ionic solids. Right, these are obviously made of ions. So for example, like your sodium chloride, your table salt is an example of an ionic solid. Remember that in ionic solids, the ions are not just bonded to one other ion, but by all of the surrounding ions. So for example, every sodium plus is actually bonded to about 6 chlorides. Remember, we said that ionic bonds are very strong, and so these ionic solids generally have very high melting points. After that, we have metallic solids. These are made up of metals. So for example, like an iron bar would be an example of a metallic solid. These can have variable melting points. It just depends on what kind of solid you have, and which that then determines the bonding. Something like mercury, right, is like a liquid at room temperature, so that obviously has a very low melting point. An iron bar, in order to melt iron, you have to get quite hot. So it really depends. And then the last type is covalent network solids. And there are other types of solids out there. There's just so many out there and so many cool things that we just don't have the time for it. But if you're interested, definitely take a look on your own. So with these covalent networks, these are held together by covalent bonds that extend kind of infinitely. Obviously not infinitely, but to a very high degree. Some examples of these include diamonds, graphite. Graphite and diamonds are both just carbon molecular solids. Carbon nanotubes, or like graphene, right? That kind of stuff. Silicon dioxide is just glass. So that's a very common one that we encounter on a daily basis. And it's a covalent molecular solid. These generally have high melting points because covalent bonds are generally strong. Not as strong as something like ionic bonds, but still quite strong. Here's just a picture of it. So in this case, these are all carbon-based covalent networks, but they don't have to be carbon-based covalent network. Diamond is just carbon in sp3 format. Graphite, like that's in pencil, is also just carbon, just in sp2 format. And so in theory, you could take your graphite from your pencil, squeeze it really, 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 really hard, and turn it into diamond. I think there's like a little skit of like Superman doing it or something like that. But you can have other types of solids as well. You can have these kind of things called buckyballs. They're kind of like soccer balls, but made out of carbon atoms. You can extend them into tubes, which is what a lot of my PhD work was on, playing around with carbon nanotubes and modifying their optical properties. You can turn them into sheets, which is basically just graphite, or you can have just a single sheet, which is graphene, which is kind of, quote unquote, like, material of the future. We'll see if it ever comes out. Overall, there's just a lot of interesting things here. You just need to know a lot more information, and it really depends on what you're dealing with. Each solid has its kind of own book of information that you need to know. And unlike gases, where all gases behave approximately the same, when it comes to solids, they all behave totally different than one another. So there's a lot of interesting chemistry and material science. So if this is something that interests you, that might be a field that you kind of want to take a look at. Material science is usually made up out of engineers, but the underlying chemistry is really important. And if you're someone who understands chemistry, you can actually, give a lot to a group of material scientists because, like I said, they're often more from the engineering perspective of something. The really cool thing about solids is if we can control their physical structure, we can affect all kinds of properties. These could be electronic, they could be optical, they could be, all kinds of properties. So for example, silicon is doped with boron or phosphorus. So silicon is added, there's some impurities added. Boron is usually an interstitial impurity. Phosphorus is usually a substitutional impurity. And when you do that, you totally change the electronic properties of the silicon. Silicon is usually a very poor conductor. It's a semiconductor. By doping it, you can make it conduct a lot better, or you can make it into an N or P type semiconductor. And then you can build these up to become transistors, which are the basis of like basically all modern computational ability, which is like the basis of, all 21st century technology pretty much. Solar cells are just basically these stacked on top of one another. You can make like LEDs out of this stuff. You can make all kinds of super cool stuff. Again, just a huge field that we don't really have time for. Silicon is generally is considered an inorganic compound, but they've been doing a lot of stuff with more organic compounds, so carbon-based, so OLEDs. Probably most of your modern cell phone day screens are made with OLEDs. OLED stands for organic light emitting diode. And so again, the idea is the same. If you can control the physical structure of your compounds, you can control its physical properties. And if you can control the physical properties, you have a really cool product, or you have some new material that can do some kind of new amazing thing. And really, like a lot of the technical improvements in like the last century or so have been from our ability to control the molecular structure of these solids.